Hello everyone, welcome to this Renewable Integration Study overview webinar on Technical Appendix A on distributed PV. This recording is intended to provide a summary of the key technical findings and actions arising from the Technical Appendix on distributed PV as part of AEMO's recently published Renewable Integration Study, or RIS for short. The RIS is a deep dive into the technical and operational challenges associated with operating the National Electricity Market, or NEM, at very high levels of wind and solar generation in 2025. This webinar on the distributed PV appendix of the RIS, Appendix A, is part of a 5-part series of webinars. Previous recordings have provided a technical and non-technical overview of the RIS as a whole, as well as episodes that delve further into the detailed findings of the other 2 technical appendices. To read the RIS publications or view the other webinars in the series, check out the major publications page on AEMO's website. My name is Rama Ganguly, and today I'll be presenting this webinar with my colleague Taru Vijalainen. We both work in the Future Energy Systems team here at the Australian Energy Market Operator, concentrating on the technical integration of distributed energy resources. We'll get to what they are shortly. So on to what we will be covering today. This topic has been the subject of some interest since the RIS was published at the end of April. Today, we're hoping to get into a bit more detail and perhaps clarifying for some the findings and recommendations from our work. So today, we will go through Appendix A of the RIS report as follows. Firstly, some key concepts that will underpin much of the technical content to follow, including what we mean by distributed PV, the increasing contribution and impact of it on our electricity system. Next, we'll talk about the questions we've investigated and the approach we've taken to explore these questions. Thirdly, we will go through in some detail the analysis we've done and key findings and implications. And finally, we'll summarize what we've covered and set out priority actions going forward. Now I'll hand over to Taru to cover some key concepts.
Thanks for that, Rama. So to start, let's look at the key concepts that we need to understand on distributed PV. So firstly, what do we mean by distributed PV or DPV? By this, we are referring to solar systems that convert solar irradiation or the sun's rays into electricity. And by distributed, they are found spread out individually all around Australia in significant numbers. The terminology DPV covers a variety of solar system sizes. This includes those found on people's rooftops, known as residential PV, through to solar on retail stores or office buildings, or commercial PV, and then up to 30 megawatts, such as solar systems on shopping centres, referred to as industrial PV. There are also really large-scale solar farms greater than 30 megawatts, but these are not included under DPV. DPV has seen an enormous growth across Australia over the last decade. We are actually at the forefront of this growth internationally. What started small in 2009 with only about 10,000 systems installed across the NEM with a combined capacity of 35 megawatts has now grown to over 2.2 million systems, and combined at about 9 gigawatts is easily larger than the single largest generator in the NEM, which is 750 megawatts. The incredible growth in this form of generation is something we can all be proud of. It has come about through the decisions of millions of individual households and businesses and has contributed significantly towards the decarbonisation of our energy supply chain and reduced energy costs for many. And this growth is not expected to slow, with the amount of installed DPV anticipated to almost double to 19 gigawatts by 2025. So combined, will make it 25 times larger than the largest generator in the NEM and could at times provide up to 50% of all demand needs instantaneously. Before we move on, I do want to recognise that DPV is a subset of systems called distributed energy resources. That includes devices like batteries and electric vehicles. Whilst these DER devices are important, they have not reached the same penetration levels of DPV, and hence the focus of this study is on the integration of distributed PV. These other forms of DER can definitely help with addressing some of the technical challenges associated with increasing DPV levels, and we will touch on these throughout the webinar where relevant. Now, to understand how DPV and AEMO fit together, we have a simplified view of the electricity supply chain. This shows a view of what the electricity grid traditionally looked like. In this case, electricity was made by large-scale generators, as you can see on the left, then transported vast distances across transmission lines. Once it is closer to areas of use, it is stepped down to the distribution network to be transferred to each customer first via their meter for billing. The customer then consumes the electricity. But now DPV is disrupting this flow. Instead, in the millions, DPV is being installed on rooftops. And now, electricity is flowing in the opposite direction. The DPV and the household sit behind the meter, and its contribution is not fully visible. With electricity flowing in the opposite direction, it creates some challenges for the power system. And Australia is now at the point where the scale of this contribution is leading to an internationally unique combination of technical challenges that ultimately are impacting the bulk system operation. AEMO is a bulk system operator for the east and the west coast of Australia. And one of our key functions is to balance how much generation is supplied to meet consumer demand at every instant of the day. But when generation also comes from the end of the supply chain, it adds complexity in managing the power system. If we want Australia to continue growing to the levels of DPV that we anticipate, we need to integrate it into the power system as if it were a large-scale generator. So now, to better understand some of the challenges, it is necessary to touch on the fundamental characteristics of these devices and what makes them different to large-scale generators. On the left side, we can see what makes them different to traditional generators such as coal and gas. Firstly, conventional thermal plants are often driven by large spinning masses that are all synchronized to the power system frequency. But DPV is connected to the power system through power electronic devices known as inverters. These inverters convert the power from solar, which has no spinning mass, from DC to AC, so it can be supplied onto the grid and then used by appliances in your house. These inverters are important as they define a lot of the characteristics in how a DPV system interacts with the grid. Because DPV is connected via inverters, they are not inherently synchronized with the power system frequency, so we refer to them as asynchronous. We see similar characteristics in some larger scale plants, such as wind farms, so this more general behaviour is discussed in the webinar on managing frequency, or Appendix B. Next, what differs DPV to a large thermal generator is that it is variable. Since DPV relies on the sun to be shining, its output is not guaranteed. Unlike coal, gas, or hydro, which we can stockpile or pump, it is variable energy that depends on local weather conditions. Since we have other generators that operate like this, such as large-scale solar farms over 30 megawatts, this will be discussed more in the webinar on variability and uncertainty, or Appendix C. And then thirdly, these devices are decentralized. So they are located at households all across the network, which means we have millions of small decentralized generators dotted everywhere. This characteristic not only makes DPV different to thermal generators, this also makes DPV even more unique than wind and large-scale solar. This is where it adds increasingly complexity from the bulk system operator's point of view and is the focus of this webinar. The key characteristics of decentralized power are listed on the right-hand side of this slide. First is visibility. I mentioned DPV is behind the meter, so we have little to no visibility of how much it is generating at any one moment. We use lots of estimates based on a sample of systems and historic data, but this has its limitations. The lack of visibility becomes challenging as sudden changes such as cloud cover over Sydney or even a solar eclipse, which we will see in 2028, reduces our situational awareness and ability to respond as required. Next is the expected performance of DPV. Currently, DPV generation is not subject to the same grid performance expectation as large-scale generators. So how they respond to fluctuations in the power system is uncertain, or the defined behaviour through the inverter is not aligned to the needs of the power system and could actually make events worse. So the performance and capabilities are a critical component for DPV to be integrated into the power system. And then thirdly is controllability. So this refers to the ability for a generating unit to respond to instructions from system operators to adjust their output. DPV currently operates following the availability of the sun. However, to operate a power system where we have limited ability to adjust generation is very challenging, especially under emergency situations like during bushfires, where the poles and wires could become vulnerable. These three elements together make DPV what we call passive. From a system operator's point of view, it is this passive nature that poses additional challenges to the power system. If we want to operate in a state where a large proportion of our generation is from DPV, we need to improve these characteristics so we can rely on them the same as we rely on large-scale generators. So this brings me to why DPV is of interest to AEMO as a bulk system operator. So when there are small quantities, it is okay that DPV is passive, like a tiny splash of water won't ruin your outfit. But in aggregate, it becomes enormous, like adding all of those water droplets into a wave. And for you, that would be very noticeable if you're standing underneath it. And it is this impact that DPV in aggregate has on the power system. To better illustrate what I mean by this impact and what this looks like, we have a chart here of a demand profile for a single day for South Australia. So on the x-axis, we have the time of day, starting from early in the morning to the evening. And on the y-axis, we have the demand for a region. What is indicated here by the line is the underlying demand. This shows the amount of electricity demand by households, commercial businesses, and industry all added together. This is representative of the historical daily profile that we used to see. It shows demand changes is somewhat flat and the minimum happens overnight or very early morning. We often refer to this as the underlying demand. But what we are seeing is that due to DPV generation, the daily profile is looking more like the purple area. This area represents what AEMO needs to dispatch from large-scale generators, or what we call operational demand. What this shows is that DPV in yellow is eroding the operational demand in the daytime, creating new challenges like new minimum demands and ramping up and down in the morning and evening peaks. Through this webinar, we are trying to understand how to manage the power system with this operational demand profile and how this will change as more DPV is added. So now that we understand the basics of DPV, I will now hand back to Rama to step us through the approach we have taken for the analysis.
Thanks, Drew. This is first and foremost an assessment of the technical challenges associated with increasing DPV generation. To this end, we've looked at three key questions as laid out on the left here. First, what are the challenges we're talking about and to what extent are these challenges impacting the power system today? Then we've asked the question, given the range of plausible scenarios for projected DPV uptake into the future, how might we expect these technical challenges to materialize out to 2025? And then lastly, we've laid out the range of measures that could assist with managing these challenges into the future. You might be wondering, why is this important? As Teru alluded to before, the passive nature of the DPV fleet makes integrating increasing amounts of it challenging, both for ourselves and the distribution network operators. Local and international experience with the mass uptake of consumer devices interacting with the power system in a passive way, for example, air conditioners in the decade from 2000 to 2010, indicate a very typical trajectory of integration challenges as uptake increases. This is reflected on the right here. Impacts first arise within the distribution networks. At low levels, they're relatively easily accommodated with little restriction or intervention. As uptake increases and local clusters start to form, limitations start to arise in the low voltage part of the distribution network, the poles and wires you can see passing through your street. And eventually, as clusters grow, impacts aggregate up the chain. Continuing with the road analogy, you start to see congestion at the equivalent of arterial roads linking different suburbs and intersections with motorways. So thus far, these impacts are quite location specific, depending on the size and location of DPV clusters in the distribution network. The first part of our study is focused on these aspects. Eventually, the size of the combined DPV contribution at the regional level becomes so significant that it impacts almost all our core duties as the system operator, namely balancing the system, maintaining stability, as well as recovery and restoration following major system events. We expect the consumer-driven revolution that is DPV uptake here in Australia to continue into the future. This study lays out the trajectory of system issues associated with this uptake. In doing so, it lays the groundwork for the coordinated planning and system design thinking necessary to address these issues in a way that best optimizes these resources within the broader integrated power system. The actions we propose at the end of this study, we think, are no regrets actions that will help to minimize the system-wide impacts of increasing levels of passive DPV, integration costs that all end users will bear, not just those with DPV systems. And in doing that, we think they'll help to maximize the potential value across the whole system of this valuable resource. Now on to the analysis. As just discussed, we've split the study into two core areas, the distribution network and the bulk power system. I will start with implications for the distribution networks before handing over to Teru again when we get to the bulk system. So first, what is the distribution network and who are the key players in this space here in the national electricity market? Distribution networks are the poles and wires historically designed to transport electricity generated in the bulk system down to end users. They consist of substations and feeder paths successively stepping electricity down for efficient and safe reticulation. This journey is summarized in the middle panel you can see here. The vertical lines represent overhead lines or underground cables. The horizontal lines represent a given voltage level. We've marked here typical voltage levels at each point here in Australia. And the symbol with the two overlapping circles is a transformer, which converts voltages between levels and sit within substations. Electricity is tapped off the transmission network, which you might think of as the interstate highway network, from dedicated connection points. We're now in the high voltage part of the distribution network, which you might think of as motorways linking and sometimes running parallel to these interstate highways. Then you take the exit from the motorway onto your suburban arterial road, the medium voltage part of the distribution network. Eventually, you get to the turnoff into the smaller residential streets that take you to your house. This is the low voltage network. Service mains then connect the house to the low voltage path, as you can see with the little house down the bottom here with a DPV system on its roof. On the right, we've got a map of the NEM with the 13 different distribution network service providers, or DNSPs, marked roughly by the areas they serve. At this point, we'd really like to acknowledge the great support we got from the DNSPs in putting this part of the study together. We very much look forward to continue working collaboratively on these important questions into the future. The biggest thing to note is that there are significant differences both within and across DNSPs in terms of the distances their networks have to serve and other physical and electrical characteristics. Some are predominantly rural, some almost exclusively city and urban, and others a mix of both. This is important because city and suburban networks are typically more interconnected, span shorter distances, with end users more densely located, allowing them generally to be able to host more DPV generation compared to rural situations with single long spokes with end users much further apart. As Teru alluded to before, there are now times where DPV generation is exceeding local demand in parts of the network. So what does this mean for distribution network operation? What are the key challenges we're talking about? The first is managing the voltage profile. So voltage is the electrical equivalent of pressure in a water hose. DNSPs are responsible for making sure this pressure stays within an allowable range and quality of supply. DPV generation in the middle of the day, when underlying demand is low, is leading to reverse flows and voltage rise. On the flip side, networks still have to manage voltage drops that occur when flow is highest in the forward direction, that's during the evening peak. Managing this increasingly wide range of operating scenarios is probably the most significant challenge today amongst the DNSPs. The next challenge is managing the actual power flows in the network. This needs to be within permissible loading levels of different network elements and basically determined by how hot equipment gets, so referred to as thermal ratings. Typically, DPV systems along a street will experience the solar peak at the same time in the middle of the day when the sun is shining brightest. With peak demand in the evening, there is generally a level of diversity across different end users. Not all are likely to have their air conditioners on at the highest setting at the same time, for example. This means that the solar generation peak can occur more frequently than the peak demand one, which typically only occurs a handful of times a year. Lastly, we have implications for protection schemes within the distribution network. Protection schemes provide a level of security in the event of faults in the distribution network. For example, a car hitting a telegraph pole. These schemes are designed to prevent the impact of the fault spreading too far and potentially damaging more assets, thereby minimizing potential downtime and helping the DNSPs restore the system as soon as possible. DPV introduces flows in the reverse direction, and this can impact the ability of legacy protection mechanisms to discriminate between faults and normal system operation. Our report goes into some detail about how and to what extent DNSPs are experiencing these challenges today. Through our engagement with the DNSPs, it's apparent that pretty much all businesses are beginning to experience voltage management challenges in their low voltage networks and often in the wires connecting the premises to the low voltage assets. Significant clusters of DPV generation in certain locations are beginning to cause voltage coordination challenges in higher parts of the distribution network across several DNSPs. The scale and nature of these challenges differs across networks depending on local DPV penetration levels and specific network factors, but it's generally the regions with higher penetrations relative to local load and network capacity, such as South Australia and Queensland, that are experiencing the most material challenges today. All DNSPs are planning for continued uptake in DPV generation out to 2025. This leads us to the next question. What are the technical solutions available to DNSPs that would enable them to host more and more DPV generation? DNSPs reported to us the measures they are implementing today or planning to implement soon to assist with integrating more and more DPV. These are summarized in a bit more detail in our report, first by the specific challenge they address in section A 3.3 and then in a consolidated way in section A 3.4. Crucially, these aren't all or nothing. A suite of options will be necessary to incrementally improve hosting capacity over time, spanning the range from passive set and forget type actions to more dynamic, flexible strategies that can accommodate the changing load and DPV generation profile over the course of the day. Network strategies, on the left here, refer to investments within and on the network itself, including remediating and reconfiguring existing network assets, selectively increasing network capacity in specific locations, or adding grid-scale storage in parts of the distribution network. And lastly, measures to enhance flexibility, essentially allowing a level of dynamic adjustment to accommodate changes in load and generation patterns through the day. There are also behind-the-meter strategies which harness resources on the customer side of the meter. These include things like changing settings or limiting export from DPV systems, actively managing the DPV generations, essentially to lop off the peak to within the limits the network can accommodate, and lastly, activating other forms of DER in the low voltage network, such as load and storage devices, to soak up excess DPV generation in the daytime. Keep these in mind because the same set of solutions will have a role to play in addressing the bulk system challenges we're going to cover shortly. Visibility is a key enabler for DNSPs, specifically visibility of their low voltage assets and the impact DPV generation is having to be able to efficiently implement measures across both of these categories. Importantly, this isn't just real-time data. It's also about access to sufficiently granular monitoring data to make informed decisions. So what does this mean for the bulk power system? Given the work the DNSPs are doing and the fact that limits are most likely to be most relevant in isolated locations in the network, we consider that distribution network limits aren't going to materially restrict the increasing DPV generation at the bulk system level out to 2025. With this in mind, I'll hand over to Teru now, who's going to walk through the bulk system challenges.
Now that we have understood the challenges at the distribution level, we now want to look at the bulk system challenges. So from Rama's discussion on the distribution network, it is clear that DPV will begin to impact AEMO's functions as the bulk system operator. So AEMO's role in this is to balance the supply and demand of electricity continuously and instantaneously. This is important as electricity cannot be readily stored to the capacities that we require for the amount of electricity needed to run the power system smoothly at every second. To help us to achieve this balance, we monitor the health of the system through frequency, which we try to balance for the NEM at 50 Hz. If we have more load coming online, like air conditioning during summer, we add more generation to supply. And as the summer day gets cooler and people turn off their air conditioning, we remove that generation. Without properly balancing the power system at 50 Hz, this can cause damage to equipment or appliances. Eventually, this could ultimately lead to disconnection of generation or load, and in the worst case can start to trigger further disconnection, leading to a system black. So this is the case where part of a region has no electricity. This can take hours or even days to resolve and bring back up to normal. To balance a power system, AEMO dispatches generation to match the demand every 5 minutes. In between the 5-minute dispatch intervals, AEMO also manages the balance through frequency control ancillary services, or FCAS. This includes through regulation FCAS, which is a correction of the supply-demand balance in response to minor deviations, or through contingency FCAS, where for more major disturbances, such as a sudden loss of a generating unit, major industrial load, or a large transmission element that results in a noticeable frequency deviation, rapid injection or removal of electricity is used to correct the imbalance. This can be achieved through generator governor responses, load shedding, or rapid generation from a fast-starting generator. So to better understand the concept of the supply-demand balance and the impact that DPV is having on this balancing equation, we will use this simple supply-demand balance seesaw to demonstrate the various challenges. But first, let's step through the basic concepts so we can build on them later. As you can see, we have the demand on the left-hand side of the seesaw. This includes households and industry, like manufacturing businesses. And then on the right-hand side, we balance the demand by dispatching supply from generators like coal, thermal, and wind. Now let's see what happens when we add DPV. What we are finding is that households are choosing to install DPV or solar panels on their rooftops. And from AEMO's perspective, even though they are installed on the demand side, they are adding generation. So in terms of our supply-demand balance seesaw, they are considered on the supply side. As mentioned earlier in the webinar, these systems are behind the meter, so we cannot see them or control them. So effectively, it is like a black box for us. When more DPV is installed, this black box grows. So to keep the balance, AEMO dispatches generators every 5 minutes, and in some situations, we actually need to start reducing other generators that are online. So based on our estimates of the size of the black box, we can constantly keep the supply-demand balance in check. We will keep referring to this supply-demand balance as we consider the various challenges that DPV has on the bog system. So what are the operational challenges that DPV is having on the power system? The first impact is the response of DPV during a power system disturbance. With penetrations of DPV, we need to understand how they respond to events such as sudden fluctuations in voltages. As DPV grows, their aggregate response becomes more apparent, and therefore understanding their response becomes more critical. Knowing whether DPV disconnects following events helps to determine the potential contingency size if mass DPV was to disconnect in concert following an event. The next impact DPV has on the power system is the ongoing reduction in operational demand. This is simply that more DPV erodes the operational demand during the middle of the day. This in fact presents some key challenges as there are limits in the power system to minimum operational demand. This includes requiring a minimum level of synchronous generators online for other system services that cannot be served by DPV. Also, for our emergency mechanisms that are utilised following a sudden event, we require a minimum level of stable load online. Otherwise, these protection schemes may not operate as they were intended. At the transmission level, high levels of DPV operation can displace the operation of utility-scale generation, which may be providing reactive power services. Additionally, high DPV generation reduces the loading of transmission lines, and as a consequence, network voltages increase, which can eventually exhaust network voltage management measures, such as transformer tap changing and reactive plant switching. The next impact to the power system is the fundamental characteristic of DPV in that it responds to solar irradiation and is therefore a variable form of generation. This means that DPV needs to be considered in the daily ramp requirements as solar comes online in the morning and goes away in the evening, and this behaviour needs to be accounted for in dispatching large generation. This can be more complicated, particularly during sudden cloud cover over a metropolitan area that can also rapidly change the ramp requirements, but also during rare events such as a solar eclipse, which would also have impacts on the ramping needs. Finally, DPV is a source of generation that cannot be curtailed. This creates challenges as DPV continues to grow and we have no other options but to curtail large-scale generation to meet the supply-demand balance. This means our power system dispatchability function is heavily reduced and we can no longer match supply and demand. This will be a significant challenge during extreme abnormal situations such as bushfires or sudden electricity events such as loss of an interconnector, and will mean our operational levers during these situations are severely compromised. We will provide more detail on these challenges in the remainder of the webinar, but there is also further information available in Appendix A, Chapter 4. Before we launch into more detail on the challenges, let's look at how DPV is anticipated to grow over the 5 years. This will help us to understand which regions we anticipate will see which challenges. So what we are showing here is the instantaneous penetration of DPV as a proportion of underlying demand for the NEM. Each coloured dot represents a half-hour period within a year. This is an important graphic and one that we will build on through the remainder of this webinar, so we will take a moment to step through the basics. On the x-axis, it shows the instantaneous DPV penetration against demand. So as we move along the right, it means that more DPV is contributing more to meet demand, and where many of the challenges will arise. On the y-axis, we show what the underlying demand is. So as we move up along the axis, it shows increasing demand. The dots represent a half-hour period within each year and therefore compare the scatter of potential DPV contribution against underlying demand. The dots that appear along the y-axis show nighttime, where there is no PV contributing, but there is still load on the system. Then on the right-hand side of the chart, that shows where a lot of solar is being provided. At the top, that's where we have high demand periods, such as during summer, where lots of aircon is operating and meeting that solar. But near the bottom of the chart, that's where we have low demand, but high solar, like a spring day where there are fewer aircons online, but lots of sunshine, and therefore low operational demand. In grey, we have the 2019 actuals, which shows that we are already at 25% instantaneous penetration of DPV at times. In red, we show a forecast out to 2025. This is based on our central scenario in our Draft Integrated System Plan, or ISP. And we can see that we are expecting DPV to grow and will exceed 35% instantaneous penetration at times. For comparison, in orange, we also see our forecast out to 2025 for our Draft ISP step change scenario. This shows that we could be reaching 50% instantaneous penetration in the NEM for a good portion of the year, and we need to operate the system between 25 to 50% for a fair number of half-hour periods. And this is a new operating territory for us. What is apparent in this figure is that in the space of 5 years, there is potential for significant change and growth in DPV, and hence the need to investigate the challenges and potential limits associated with these technologies, and the possible actions needed to adapt to these operating conditions. Now, before we move on, in this slide, we are showing the same chart, but separated by each region of the NEM. So what we can see here is SA is leading the way with the potential for times to already be over 75% instantaneous penetration. This becomes even more important as SA can be electrically separated or islanded from the rest of the NEM. If this occurs during these high instantaneous DPV penetration levels, this puts SA in unprecedented operating territory, and what we expect is that DPV growth is expected to continue. The other regions, so Victoria, Queensland, New South Wales, and Tasmania, are all following the same trajectory. And what the figure shows is that each NEM region is projected to be frequently operating with significantly higher penetrations of passive DPV generation than today. These charts will provide the foundation for the remainder of the presentation. Now Rama and I will delve into more detail on each of the challenges that will be experienced.
So starting with these regional projections as an indication of plausible futures that might eventuate to 2025, we've identified 3 key zones that kick in as DPV penetrations increase and impact our operation of the bulk power system. Zones have been identified based on extensive work we've done to date for the South Australian region, which is the NEM region at the forefront of DPV integration challenges today. As we work through these zones, Taru will come in and talk us through a relevant South Australian case study using the same balancing scales framework she presented before. This is all discussed in a lot more detail in section A 4.4 of our report. The first zone we've identified corresponds to when DPV penetration crosses the 20% mark. From this point, DPV is beginning to noticeably impact the system load profile. As penetrations continue to increase, specific operational challenges may arise. So increasing levels of DPV online during low underlying demand periods begin to impact the availability of stable load blocks, which are necessary for these emergency mechanisms to work properly if rare, high-impact, low-probability events were to occur in the daytime. The 2 key mechanisms we're talking about here are emergency frequency control schemes, as well as system restart. Next is transmission voltage control. So reducing daytime load, as seen by the transmission network in locations with sufficiently large clusters of DPV generation, starts to impact how voltages are managed within the transmission system. The purple line on these charts traces out historical nighttime minimum demand levels. So we've shown this because voltage control challenges have historically occurred in the middle of the night when demand is very low and not much synchronous generation is online. Minimum operational demand occurs in the daytime today in South Australia and Victoria. Out to 2025, almost all NEM regions will now be experiencing those similar conditions in the middle of the day. The last challenge that's relevant in this zone is around net load variability. So this is to do with the variability of solar generation through the day. So both variability due to cloud cover, as well as the typical diurnal pattern at the start of the day and at the end of the day. So operationally, sufficient flexibility is required to be able to cover this variation in the DPV generation. Cloud movements are especially challenging given that they are faster and less predictable sources of net load ramps and can be a challenge at specific points in the network for voltage control. Now over to Teru, who will go through a case study from South Australia today, looking at one of our most critical emergency mechanisms.
So to illustrate Rama's point on stable load for emergency mechanisms, we will look at a specific case study on the effectiveness of the under-frequency load shedding, or UFLS scheme, and why this is challenged as DPV grows. This is a protection scheme that operates at the distribution feeder with the intention to trip load in response to a sudden loss of generation and rebalance the seesaw and keep the system stable. Looking at the seesaw balance once again, as previously shown, these houses on the left have solar, but this is instead represented in the black box on the supply side. This scenario takes place during low load conditions but lots of DPV generating, such as in the middle of the day during a sunny, mild spring day. Following some unrelated but plausible reason, a generator may trip and disconnect. We can see this as the icon goes grey. The supply side becomes lighter and the scales tip. Frequency reduces into the red zone. So where the frequency drops significantly, the UFLS scheme may autonomously activate frequency-sensitive relays in order to rapidly rebalance the supply and demand. However, if a lot of the load has distributed PV associated with it, these feeders could be operating as net generators or in reverse flows. This means that in net terms, that the houses in a street are generating more from solar than they are consuming. So we have not only turned off some demand from the houses, but we've actually turned off more supply coming from the DPV as well. Instead of solving the issue, this actually exacerbates the supply-demand imbalance. This means the supply side may be even lighter, and the scales tip even further into the red, and may mean the system is not stable. This could lead to further load shedding, cascading failures, or in the worst case, a blackout. As more DPV is connected, the amount of stable load available for emergency mechanisms is reduced. Looking at South Australia, which as we noted is already at high DPV penetrations, we have identified that there are periods today where under low inertia conditions, if a large contingency event were to occur, UFLS in South Australia may already have insufficient load to shed to arrest a frequency decline. By December 2021, if no action is taken in South Australia, up to 85% of all UFLS stages, that means the trip frequency bands, could be in reverse flows in certain periods. If the scheme was enacted, this could instead exacerbate the disturbance, possibly leading to a black system. And by 2025, other NEM regions are projected to also experience periods with less availability of stable residential load, with further investigation required. For more information on this case study, please refer to Appendix A, Section 4.2.2.
Now on to our next zone, which is Zone B, marked in the blue in the charts you can see. From this point, the potential mass disconnection of DPV systems begins to materially impact the effectiveness of contingency management practices. Over the last 18 months or so, we've developed a considerable evidence base demonstrating that a significant portion of DPV generation can disconnect following plausible disturbances in a transmission network. So the boundary between Zone A and Zone B signifies the point where the loss of DPV generation might exceed potential load disconnection following plausible transmission disturbances. If this takes place at the same time as the loss of a large generating unit, it could potentially result in a contingency size exceeding the largest credible risk in the region. Beyond this point, additional measures will need to be in place to manage these impacts. Eventually, the net contingency size may become unmanageably large, especially for regions of the NEM that can operate as an island under some conditions. So that's reflected in the other solid blue lines as you move to the right in this picture. The 50% and the 100% are with reference to the largest credible risk that's managed today. Again, over to Taru, who will talk us through a significant challenge in the South Australian region today around the risk associated with DPV systems disconnecting in case of a fault in the Adelaide metropolitan area.
So looking at the supply-demand balance again, now we're looking at a specific case study for an event in South Australia. Once again, the DPV is represented as a black box on the supply side. If there is a loss of a generator such as Torrens Island, which is near the Adelaide metropolitan area, and this in turn creates a resulting voltage event, we can see this loss of generator disconnect as it goes grey and the supply becomes lighter and the scales tip. In response to the transmission level voltage disturbance, we have found that up to 40% of DPV consequently also trips, as you can see as the black box becomes smaller. As a result, the scales tip even further than expected, so the DPV trip-off in fact exacerbates a supply-demand imbalance. AEMO has done extensive analysis on these disconnections, and there is now considerable evidence to show that DPV consistently disconnects to a voltage disturbance based on its vicinity to the voltage event and its severity. The power system is designed to operate to withstand disturbances resulting from what we refer to as credible events. This refers to the loss of a single element, such as a single generator. Operationally, we withstand the disturbance through constraints in the dispatch process and procurement of ancillary services. But by adding the loss of DPV to the loss of the largest generator, the contingency size becomes greater than what we would normally plan and procure for in these normal credible events, meaning AEMO has limited effective tools available to manage this additional impact on contingency sizes. The availability of these tools are even more limited when South Australia is operating as an island, as they can't be sourced from other regions. So when South Australia operates as an island, if a severe voltage event in the Adelaide metropolitan area coincided with high solar PV generation that triggered PV disconnection, the ability for AEMO to arrest the event would be impacted. For more details on this case study, please check out section 4.1 in the Appendix A report. I'll now hand back to Rama to go through Zone C.
Thanks, Drew. So now on to Zone C. Zone C marks the point where operational demand has reduced to such a level that there's not enough load to support minimum synchronous generation requirements. As discussed previously and in other webinars in this series, a certain level of synchronous generation is required to be online at all times in order to have sufficient essential power system security services available. The provision of required system strength, inertia, and frequency control ancillary services is the limiting factor in this case. This provides a hard limit to DPV generation online. If and when we were to get close to this point, we have very few levers available as we cannot reduce DPV generation. Taru will now go through a case study for the South Australian region that demonstrates the urgent need for sufficient backstop mechanisms to be in place if quite extreme abnormal system conditions were to take place during periods like this.
Thanks, Rama. So now, once again, let's look at the supply-demand balance in this scenario. So eventually, as penetrations of DPV grow, we will see significant penetrations in the middle of the day, where DPV is generating at its maximum. In the case where we have a loss of interconnection to other regions, we have no options to export this excess DPV generation. This means that all supply and demand needs to be covered within a region itself, which can occur in South Australia when it becomes islanded. So in this case, there is high instantaneous penetration of DPV and low demand, as you can see with the DPV black box growing. Once again, this is represented on the supply side as they act as generators. To accommodate this much DPV in the system, we then curtail or turn off other large-scale generators that are supplying generation so that we can match the remaining load. This is shown by some of these generators here switching off, such as wind. However, there is a limit to the minimum number and how low these synchronous generators can be turned down. This is because they need to be online for other system services such as system strength, FCAS, or to maintain voltages. And to be online, they have equipment ratings that require a minimum loading. This minimum synchronous unit threshold is shown by the red dotted line. As DPV grows, we can no longer turn other large synchronous generators down to accommodate the increase in supply from DPV. We also have no current means of turning DPV down either. So now any further increase in the DPV black box can now cause an imbalance in supply and demand. AEMO can try and increase demand to meet this increase in supply. However, this is not always available. This means we have run out of potential operational levers to return the supply and demand to be in balance. This means that the only way to keep the supply-demand balance maintained and also ensure other essential services are online is to reduce the DPV on the supply side. This is a last resort emergency backstop mechanism that would be necessary in order to securely manage the power system. In South Australia, since the region may be islanded and the penetration of DPV is already significantly high, we have an urgent need for DPV generation curtailment capability. Analysis for South Australia has identified that under system normal conditions, there is sufficient interconnector capability for the minimum synchronous unit requirements to be met, even if operational demand in South Australia is zero or negative. Although, under credible risk of separation or islanded conditions with reduced or no AC interconnector export available to support local FCAS enablement and inertia requirements, additional local load or PV curtailment will be required. Having the DPV shedding capability for these really rare events allows us to maximize DPV generation at the bulk system level and means we can utilize storage and load for its most efficient use, namely as source of flexibility on a daily system normal basis, and not set aside for these rare circumstances. Please refer to Appendix A, Section 4.2.1 for further details. I'll now hand back to Rama to wrap up the bulk system operations section.
Thanks, Drew. Now let's come back to the overall picture for all NEM regions. Here we've got a presentation of the zones we've just stepped through. As penetrations increase out to 2025, all regions are projected to be operating with significantly higher penetrations of passive DPV generation than today for a decent proportion of the year. Now let's turn to the range of measures at the bulk system level that can assist with integrating this level of DPV generation into the future. From a bulk system perspective, a suite of measures will be necessary to optimally integrate DPV generation into the future power system. These are summarized on the screen now and explained in more detail in section A 4.5 of our report. The dependable, affordable supply of energy is of critical importance for households, businesses, commerce and industry, and therefore the wider economy. Electricity systems generally operate to a level of reliability a step or two higher than other complex time-critical systems you might be familiar with, for example, transport networks or telecommunications. The system is designed to be able to cope with a range of operating conditions. These range from normal day-to-day operation, abnormal conditions associated with the sudden disconnection of a large generator or a major transmission path, and also extreme abnormal conditions associated with exceedingly rare events, such as regions islanding from the NEM or at elevated risk of doing so, and system recovery and restoration following major system events. We've classified measures across 4 categories below. First, on the left, measures directly touching the DPV systems themselves. Our key recommendations are in this category, so I'll come back to this shortly. Next, we have balancing DPV generation with load and storage in the distribution network and behind the meter, essentially introducing sources of demand to soak up excess DPV generation in the day. This undoubtedly will play a massive role into the future. However, this source of flexibility is not at sufficient levels today to address the key bulk system DPV integration challenges we're concerned about, especially during extreme abnormal system conditions. Next, we have system management solutions, which cover procurement of reserves to better manage the risks associated with mass DPV disconnection and operating the system more conservatively to reduce or eliminate the chance of getting into high risk or inoperable system conditions. The last category here is network solutions such as new transmission paths and interconnections between regions, which enable better sharing of DPV generation between regions and reduce the likelihood of regions islanding from the NEM. System management solutions and network development options will be increasingly costly means of addressing the bulk system implications of increasing levels of DPV generation into the future. What we've proposed in this study, which we'll touch on shortly, we think are no regrets actions that will help to efficiently integrate increasing levels of DPV in the power system in the least cost way, benefiting all end users, not just those with DPV systems. So now we've gone through challenges in the distribution network. We've also covered challenges at the bulk system level. So let's summarize what this all means. So stepping through this sequence here, first, the increasingly large passive DPV fleet has begun to pose technical challenges to both distribution network and bulk power system operation. Next, South Australia is at the forefront of these challenges today, and other NEM regions will be increasingly impacted out to 2025. The DNSPs are implementing both network and behind-the-meter measures to improve hosting capacity. Visibility is a really critical enabler for this to take place the most efficient way possible. A suite of measures is required to optimize the integration of DPV within the power system for the benefit of all end users. Next, last resort mechanisms to manage rare and unexpected events are critical for this optimized outcome. Now we've landed on our key recommendations, which are to do with enhancing the performance of the future DPV fleet and an ability to curtail DPV generation if required. So to summarize, we had 5 key actions coming out of this study. Our actions are summarized across the 2 categories you can see in the first row here. The first is to do with the performance of the DPV fleet during disturbances, which is a critical issue in South Australia today and will be increasingly important in other regions going forward. This is to do with improving performance standards so that DPV systems respond in a supportive way to fluctuations in the power system and in a way that supports system security. In the long term, having these measures in place by reducing the overall system integration costs associated with managing mass DPV disconnection will reduce the system integration costs for all end users. On the other side of this figure, we've got a minimum level of curtailability for DPV generation we see as being part of emergency backstop mechanisms necessary to keep operating the power system securely during rare abnormal system conditions. So this recommendation involves device level capability to be remotely interacted with during emergency situations. This will allow a significant portion of the DPV fleet to be brought into emergency control schemes designed to curtail DPV generation during rare system events. And finally here, we've got additional actions progressing outside of the RIS within our DER program and the wider industry, looking at market and technical enablers to optimize DPV generation with other DER, specifically load and storage behind the meter, and into the future, things like electric vehicles, as well as measures to improve the visibility and predictability of DPV generation into the future to enable better decisions at both the distribution network and bulk power system level. I'll hand over to Taru now, who's going to present the big picture in the context of the wider RIS.
Before I let you go, I'll just tie this back into the broader RIS landscape. So some of you might remember this chart from the technical overview webinar. If not, that webinar goes into understanding this graphic in much more detail. It shows a view of the instantaneous penetration of wind and solar generation as a proportion of underlying demand, with each coloured dot representing a single half-hour period within a year. We also have a progressive overlay of system limits and challenges depicted by each of the coloured zones and when action from each of the key RIS areas is needed to begin. In yellow, we see the challenges with managing distributed PV. This starts from about 25% penetration as discussed throughout this presentation. Given the lead time on many of the RIS actions across variability and uncertainty, system strength, frequency, DPV, and operability, a recommendation in the report is that all actions, including the ones Rama just took you through on the previous slide, need to commence immediately in order to have them in place in time to support the ongoing system transition. In combination, if all these actions are taken, we think it could be feasible to operate the NEM with instantaneous penetrations of wind and solar generation of up to 75% by 2025, which is the black line you see in this chart. However, if these actions aren't all taken, we'd expect the various system limits would cap maximum wind and solar penetration levels at between 50 and 60%. Looking to the future, AEMO has not identified any insurmountable risks why the NEM can't operate securely in the grey zone, with instantaneous wind and solar penetrations of up to 100%. Just a reminder that for an overview of the RIS or to delve into the other technical appendices, head to AEMO's website to check out the rest of the series. So that's it for this webinar on the RIS Technical Appendix A Distributed PV. Thanks for taking the time to listen and hope this was of value. Until next time, cheers.